All right, welcome. This is Unit 3.4, Special Cases. So we've been talking about factoring a lot. We started with the greatest common factor, and then we did like grouping, and we did factoring when A is 1, factoring when A is not 1, and now we're going to look at some special cases that will help us factor some more. All right, so looking at these five expressions, what do you notice? Okay, you may say, well, we all have like a variable squared, and that's true. We also notice that we have a negative for all of them. And you may also notice that all of these constants are perfect squares. All right, so when you have problems that are like this, we call this the difference of squares, which makes sense because we're doing the difference. Negative is a difference. And we have two perfect squares. Right? You could rewrite this as x squared minus 8 squared. You could rewrite this as y squared minus 5 squared, or x squared minus 7 squared. So we could write these as perfect squares. All right, so looking below, that has a difference of perfect squares. We have this little equation that whenever we see something like this, we can automatically write our factored, fully factored expression. All right, so one of the easiest way I feel to be able to solve these problems, or just to factor these problems, is just to realize that if we wanted to rewrite this as a b squared, well, basically what we'd do is we would take the square root of 16, because the square root of 16 would give us 4. Okay, and now it kind of looks like what we're looking for. Okay, even easier, you could probably, or you can, just take the square root of the first term and the last term. All right. Again, this always has to be like the ax squared kind of thing, and this has to be your c part. If you have a bx, like if we're doing standard form ax squared plus bx plus c, if we have a term like that, then we cannot use the difference of squares. Okay? So if we simplify the square root of x squared, well, that's just x. And what's the square root of 16? Well, that is just 4. Okay, and then for all of these problems, we're going to have two parentheses that have the exact same thing inside, except one is going to be positive and one is going to be negative. And if you don't believe that this is correct, you could always FOIL it back out. Okay, you don't need to do this, but if you wanted to check, you could. That would give us x squared. Here we'd get a negative 4x, a positive 4x, and a negative 16. And as you notice, like terms would cancel out for the middle term, and we'd just end up getting x squared minus 16. We're going to square root first term, last term. Square root of 9 is 3. Square root of x squared is x. Square root of 25 is 5. Okay, again, we're going to have the same thing in both parentheses. The only difference is we're going to have a positive and a negative, so that the middle term would cancel out. All right, C, same thing. Square root, we get x plus 10 and x minus 10. D, square root, got 10x plus 1, okay, and 10x minus 1. Okay, so I've had some students say, well, what is the square root of 1? Well, it's always going to be 1. It's just like if you have 1 times 1, that's 1. Okay, that would be the same thing as 1 squared. Well, 1 squared is 1. Okay, if you're going backwards, if you take the square root of 1, it would still be 1. Okay, I don't know if that makes any sense. All right. So let's do some other examples. Okay, sometimes we'll have the difference of squares, but if we look at e, that doesn't look quite right. If we took the square root of that and took the square root of that, that would not look very nice, okay? So the first thing we would want to do is take out the GCF, the greatest common factor. Here we can take out a 3. That would give us 3. 3 divided by 3 gives us 1, so that just gives us x squared. And negative 27 divided by 3, that would give us a negative 9. Okay, now what's in the parentheses is the difference of perfect squares. We could square root first and second term, first and last term. We'd end up getting, the 3 would still be there. We'd have x plus 3 and x minus 3. All right, so pause and see if you can do the next 3. All right, greatest common here would be 2, so we'd take out a 2. We'd have x squared minus 16. Same thing with square root. All right, and what we're doing, mathematically, just randomly taking those square roots, that doesn't really make sense. But if that helps you just to realize that's what's going to go in our parentheses, that's really what we're doing. It's just saying that's going to be our x and our minus or plus 4 and our x minus 4. All right. Again, I mentioned this before in class. These can be in different orders, okay, as long as what's inside stays the same. Okay, so if you wanted to do, this would be exactly the same as 2 times x minus 4, and then do x plus 4. So don't worry about the order of those, okay. All right, here's another example. What would be the greatest common factor? Okay, we can factor out a 5. So that would give us x squared minus 25. And after this, you don't need to do this, do the square roots, if you know what you're doing. So it'd just be 5 times x plus 5 and x minus 5. H, same sort of thing. We can factor out a 2. That leaves us with 49x squared minus 1. Right? So just make sure you're dividing each term by 2. After that, you would have 2 in our parentheses. Would have 7x plus 1 and 7x minus 1. All right? So, and always if you're doing the difference of squares, what's in these 2 parentheses will always be exactly the same except for the sign, the positive and the negative. You can never have them be exactly the same. You can't have 7x plus 1 times 7x plus 1 because that wouldn't give you what our original problem would have. Okay? All right, so that's half of what we covered. All right. You're maybe also run into problems that look kind of like this. That we have a constant that isn't a perfect square. All right, but we'll end up doing the exact same thing. We would square root the first term, would square root the second term. Okay, square root of x squared, that gives us x. And then we'd do plus x minus. Okay, in the past, our constant has been a perfect square. So like if it was 9, then when you take the square root, that's 3, and that's perfect. Okay, we can simplify it. But with the square root of 5, we cannot simplify that further. So we would just leave it as a square root of 5. Okay, this would be our solution. The roots will have been simplified as far as they can, and that's all we can do. Okay, so the same with all of these. We'd have x plus the square root of 3 and x minus the square root of 3. Okay, pause and see if you can do the rest ones that we haven't covered. Here you'd get x plus the square root of 21 and x minus the square root of 21. B, same thing, x plus the square root of 10 and x minus the square root of 10. X minus this or plus the square root of 15 and x minus the square root of 15. X plus the square root of 2 and x minus the square root of 2. All right, there may be ones that would be something like, let's come up with another example, x squared plus 20, all right? And we wanted to write that, or wanted to factor that. So you'd want to do the same thing, you'd square root first and last term. That would end up giving us x plus the square root of 20 and x minus the square root of 20. However, in this example, we can simplify the square root of 20. And we've done those before. Like the square root of 20, we could do a factor tree that gives us 2 and 10 and 2 and 5. And then the 2's would come out, the groups would come out. So really we could rewrite this as x plus 2 square roots of 5 and x minus 2 square roots of 5. I mean, these are equivalent, but this is not fully simplified. So this would be a better solution. Okay? All right, and then there's one more. Okay, I'm just going to read this. There's one more last shortcut that we can use now that we've had some experience with imaginary roots and polynomial equations. So we know about imaginaries, what happens when we multiply two imaginaries. Okay, that's kind of the hint here, is that whenever we have an I squared, that ends up giving us a -1. So to try and figure out what would happen if we had imaginaries, let's go ahead and distribute, or FOIL. So here we would get x squared minus 3i x, plus 3ix, and then we would have -9i squared. Okay, in the past we've canceled those out. We'd have x squared minus 9, but we know that I squared is -1, so that would end up giving us x squared plus 9. Right, and this is called the sum of perfect squares. Right, so before we were doing the difference, all of these were doing the difference, they're negatives, okay? But now we have problems where it's the sum of perfect squares. So the only difference really with the sum of squares is at the end we'll have these imaginary numbers that will go with your constants. Okay, so for example, we would do the exact same thing. We'd get x plus 5 and x minus 5. Okay, but if we look at that, if we were to distribute, we'd end up getting a -25. And that's not what we have in our problem that we're trying to solve. So we would need to put in an I because it's positive. And now if we were able to distribute, we would get -25i squared. And I squared is negative, so it would change its sign to be a positive 25. Okay? And if you don't believe me, just go ahead and distribute like we did before, and that would hopefully clarify any questions you have. Okay? Looks like I didn't erase these on the bottom from before. Okay? So let's go and do B. Same setup, would do square root. First term, last term, that gives us 4x plus 7. Okay, but since it's an I, we're going to put a positive, we're going to put in an I. And then we'll do the exact same thing, except we'll have a negative. 4x minus 7i. Okay, pause and see if you can do C and D, if you haven't yet. Okay, so it's square root, that gives us x plus 6, and because it's a positive, we need to put an I, and x minus 6i. Okay, and then the very last one kind of brings everything together. Okay, this would probably be the most difficult sum of different squares. Okay, was that we would need to take out the GCF first. Okay, if you notice, we can factor out a 9 and an x. what we'd have left would be x squared plus 9. Okay, if you don't believe me, you can just distribute back. All right? And then, now that we have it as the sum of perfect squares, we can square root both sides, or both terms. We'd still have this 9x, and then we would have x plus 3i because of the sum, and then x minus 3i. All right, so that is what we covered in class.